Pídele, por favor, a Richard que me pase el correo de Frank. Sí, nada, porque no lo puedo sacar. Entonces, para. Sí, se queda más. ¿Cómo se llama? Como tengo que estar cambiando de ventana en ventana. Es Frank.
Se iban a presentar a la gente también con el domingo, ¿ah, gorda?
Ya está, ya están transmitiendo entonces. No.
Sí, ya. A ver. Frank. Frank Moreno. Ah, pero ya va, yo tengo aquí el de la PU.
Ah, ya, entonces yo tengo.
Es este de ahí, ¿no? El Frank, no sé qué, en la otra hojita. No la tiene, ya se perdió en la otra hojita. Ajá. Gracias. ¿Te quieres sentar aquí mientras papi habla? Bueno, vaya, se sienta allá atrás. Así no nos se barra. A ver. Hace porras. Ah, muy bien. Mejor lugar. ¿No puedes hablar? ¿Ah? Tú eres muy tranquila. A ver. Don't talk. ¿Qué estás haciendo? Ahora lo estás conectando. Sí. Vale, a ver. Ya estamos casi sobre la hora, ¿no? Ya estamos sobre la hora. No, entonces estabas diciendo que incluso sí, sí, que no se afortunadamente no se ven ni las arrugas ni nada, no se ven.
Pero apaga tu audio.
Ay, ya perdí tu hombro.
Sí, ¿no? Mira, aquí está.
Oh, se ve alguien. Aquí alguien se ve.
Lo lograste invitar.
Lo invito, pero no me contesta.
Escriben en Gmail.
Sí.
Mira, del otro lado aquí está contestando. Estoy teniendo. Ahí. Vamos a estudiar, no me la tengo mal, la voy a leer. A ver si se puede. bueno, si quieres poquito. Cuando empiezan la sesión, no voy a poder estar hablando contigo y no para hacer algo ahí con la cámara.
¿Cuál cámara? Sí, está muy fea, ¿no? A ver, supongo que es este, ¿no? Pero, ¿cómo? A ver, fíjate. ¿Se mejoró?
Sí, un poco.
Pónmela aquí para que la... Es que tiene un tiempo de otra, tiene un tiempo de retraso. Aquí está muy helado. Y si pone que es lo que va a grabar.
Es que
Entonces, a ver.
el salón 3 está bien. Te dice enviando la invitación, ¿cómo se dice salón 3?
Ajá. Más que dice que tiene problemas con su club. Ahí está ya. Sí.
¿Aló?
¿Nos escuchas?
Sí, perfecto. Te escucho perfecto.
¿Están prendidas estas cosas? Préndelas, ¿no? A
¿Me
ver,
escucha usted?
espérame también. Bueno, ya nos escucha, a ver. Habla.
Hola, hola. ¿Me escuchan?
Ya nos escucha, pero falta que nosotros escuchemos.
A ver.
A ver, habla. ¿Qué le pediste? Sí, está prendido. A ver, si no, la traía el eléctrico.
Aló, aló.
Ahí está, ya, ahí está.
Ya, perfecto.
Ya, perfecto. Perfecto, sí.
we can wait a couple of minutes, or we can begin right now. Here is Frank Moreno, he's our first speaker today. Hi, Frank. He's going to present us the paper agreed high power factor corrector microinverter without electrolytic capacitor by the control of voltage in the DC link for a nonlinear load. Frank is Frank, just a second. Yeah, it's on somewhere.
Hi.
Hi, Frank is an electronic engineer, graduated in 2013 from Universidad Nacional in Peru. Currently, he's pursuing a master degree in control and automation engineering at Pontificia Universidad Católica del Perú. He enjoys working in robotics, Internet of Things, home automation, and power electronics. Up to you, Frank.
Thanks.
Thank you.
Yeah. Thanks. Welcome. Good day. The title is a great type power factor correction converter with electrolytic capacitor by the control of the voltage in a DC for nonlinear load. Nowadays, most of the devices introduce harmonics to the grid because they are nonlinear loads. This causes many troubles, such as malfunction of devices, overcurrent, reduction of voltage level, failure circuits, and reduction of electrical substation transformers performance, increasing the maintenance costs. Then here we have to define some concepts. The first one is the true power factor, and the second is the total harmonic distortion. Okay. The true power factor is, a difference in the common definition is it considers the harmonic influence of loads. And here are the questions. The proposed is a converter of two-stage that allows to the connection of a photovoltaic, a battery, the grid, and nonlinear loads with this link that allows the void of an electrolytic capacitor. Here I am doing a review of concepts. The first is to reduce the harmonics and reactive power. We have the power factor correcting methods. There are two kinds of power factor correcting methods: the passive methods and the active methods. In the passive, the most common method is the Schwinn filter, but in the active methods are Schwinn active filter, Statcon, and springs. The springs is one of the most innovative methods, but has in common that that requires a non-critical load. Well, in the control methods, there are many types and many criteria to design the controllers. The first one is by frequency analysis. The second one is by a complex vector proportional interrates. This controller allows a pole placement of the pole. A pole placement of the criteria design. Then exists a general resonant controller, and it has many advantages reducing the overpeaks. But in counterpart, the steady state error is not zero, and this is a principal point at the moment of designing the controller. Another type of controller is the proportional multi-resonant. This is for reduce the harmonics because it it takes many frequencies in consideration to cancel the harmonics, but it has a low, no, it has a very high cost, conventional cost. And well, the converter is this, but the DC setup is the first step, can work as a current source. Then the problem is reduced to only a BSI converter, or only an inverter. Well, this model can be described in this block diagram. Yes, sorry. Hello, can you hear me?
Yeah.
Well, I continue. The converter can be described as this block diagram, and that simplifies many things. For example, here we have a low pass filter, like the current of read, and the load. These are considered as a perturbation signals. Here are a table of the parameters considered to the design. And in this picture, the total controller is proposed. We have three nonlinear loops. The first inner loop is to control the current in the read. The second, the middle loop is to control the voltage in this point in the PCC, the common coping point of the grid and load and the inverter, and the outer loop is to control the voltage in this capacitor, in this link, because the amplitude in this capacitor is not constant. It has a perturbation, a controller perturbation. Well, the controller was designed in a continuous space, but some discretization methods were considered. The common discretization methods are to work with signals that converge to a constant value, but working with sinusoidal is not the same that working with continuous or constant value. So in this example, we have a variable, a signal x, a period signal, that with a frequency omega sub 0, and we have this signal in a frequency spectrum and its derivative. But in counterpart, we have the x key and x dot key in a time discrete time. But when we apply a derivation, in a discrete way, we don't have the same signal. So this is translated to a non-zero error in a steady state in the moment of discretize the controller. Then we have to propose a method to discretization that allows the zero error. And well, here's a new operator that we just defined. Then we call delta. And when we apply to the controller, we can verify that the zero error is achieved in the zeta plane. And then recalling the picture before of the controller, we have the values of each controller here. In this case, those controllers not necessarily work at the same sample frequency. For example, the inner and the middle loop works at 50 kilohertz, but the outer loop works at 992 hertz. because they work with different signals. The simulation result is the following. In this picture, the voltage and the current in the grid is shown. In this case, the grid is simulated with a high impedance to increase the distortions. Then and the power consumed by the grid is like this. Is that shown in this picture? And it's clear that it must be it is necessary to apply a correct factor correcting method. Then at the moment of apply our converter, we can see that the voltage and the current recover its sinusoidal current form. In this case, the red waveform is the grid current, and the purple waveform is the voltage current divided by 100 to give the same scale, and the blue signal is the amplitude needed to the current is the amplitude that the currents have to have to have an equilibrium of power. Well, in the first part of the picture, there are the DC converter is not injecting power, but in the second part is injecting 100 watts by the photovoltaic panel. And in this other picture, we can see that the power consumed by the grid. And given that the tap is not delivering power, the grid is giving all the power. So this is the way the reason that it has a big power. But when the tap delivers 100 watts, the power given by the grid decreases. You can see that the steady the steady time is very fast. And the other way, okay. This is a picture this picture shows the voltage in the DC link. It can be seen that it has a rapidly steady time, and given in this point is deliver more power by the tap, this doesn't suffer any perturbation by this deliberating. In this table, the results there are some results. Without power factor corrector, the current THD the grid current THD was 85%, and the voltage THD was 7%. But with a power factor corrector and a series battery injected by the tap, we have a big reduce of the THD, 1.8% and 0.16%. In the case of the active power, the active power has been reduced a minimum because it's the same active power, but in the apparent power is reduced to the approximately 50%. And this means a true power factor near to unity. The same results when we have the same results when we inject 100 watts by the tap, and there's this table shows a good decrease.
Hello.
Yes, continue. Yeah. Well, in this table, a unity power factor is achieved in comparison with the result without power factor corrector. Then we have a novel controller for a bidirectional single-phase two-stage converter without electrolytic capacitors, working as a power factor under an unlimited grid from connected loads is presented. The controller uses two inner loops to control the grid current and the power common point power of common point voltage inside a waveform. Besides, an external loop is used to control DC link voltage, taking as control signal the grid current amplitude according of the power delivered by the photovoltaic and the battery arrays. Simulation proof that a power factor near to unity is achieved. It shows that the proposed controller allows enhancing a time response of the grid current amplitude. In addition, the transient response is improved due to the use of the power delivered by the tap converter as a feed-forward signal. Finally, design criteria obtains a reduced order controller which guarantees a low computational cost. Thanks.
How do we proceed? Yeah. Thank you, Frank.
Thanks for you.
Question? No? Dear Frank, you are presenting a simulation. Why are you discussing this kind of controller? What kind of framework are you using?
The simulation were testing.
Sorry?
The simulation were made with PSIM.
Yeah. But why are you using this discrete controllers? I don't understand.
Oh well, the controllers in literature are with high computational costs and has many how can I say? Has many problems. The idea of this controller is to reduce the computational cost and increase the increase the true power factor. There wasn't a complete solution in this area.
Yeah, thank you. We, if there is no more questions, well, we are going to thank you, Frank. Thank you for being here. Sorry, well, we didn't miss each other. Thank you very much.
Thanks. See you.
Well, bye. Bye. Yeah. Okay. Well, I am in fact the next speaker, so we have to change some couple of things here. Yeah. No. Okay. You have to stand for the next speaker. You have to stand up here to take in the video. So, well, I would like to thank you for being here. I know it has been well, here because of the active Mexico City. Well, as a biography, I am going only. I just want to say I'm a proud father of a 6-year-old daughter. So that's it. I'm going to show you a nice about integral control in DC to DC power converters. I am working at the Universidad Tecnológica de la Mixteca here in Oaxaca. We are going to cover in this presentation an introduction. We are going to speak about the power PWM power converters, DC to DC power converters, some singular perturbation, how this is kind of approach of singular perturbation approach and to work with the stability, and what is current mode control in Greek. After that, we are going to speak about symptotic stability of this slow and fast path using integral control of this kind of DC to DC power converters. At the end, some experimental results, and finally some conclusions. Why stability in DC to DC power converters is important? I think, because of application. There are a lot of applications of PWM power converters, DC to DC power converters, in industrial, factory automation, building automation, avionics, and automotive. Aided systems, lining and power training. You know, now everyone is talking about electric cars, so they are there. PWM DC to DC power converters. In the case of personal electronics, now this is a kind of very current research of wearables, tables, gaming, and communication equipment, servers, telecom infrastructure, wireless, or if you have a complete system with processor, any reference, has to be work with this kind of PWM DC to DC power converter. So, what is current mode control? Current mode control is a nice strategy. It's a two-loop strategy. We are supposed to have an internal loop control using maybe switch or inductor current, and you have an external outer loop measuring voltage. In this case, the design is based in the following. What you're going to do is to make this internal dynamic faster than the outer dynamic. This kind of controllers come from 1978 with the work of Sage, and after that Capel and others. But if you are going to IEEE explore, you can find a lot of reference working with these are 1,100 references only working current mode control and not working current programming control. There are a lot of names of this kind of strategy. This is then current mode control. What is a singular perturbation approach? I'm going to relate this to the previous slide in the following way. The singular perturbation approach is based on the following. We are going to have a fast dynamics, and a slow dynamics. The faster dynamics with this kind of fast parameter epsilon. In this case, in the limit, epsilon is going to have the value 0. If you have this as 0, you obtain this equation, and well, you are supposed to express here x in terms of c as a function with, for example, one value, or at least in a neighborhood. And well, when you have this expression, you can replace here x, the value of x, by this expression here, and obtain a flow system, which is called quasi-static state mode. If you think about current mode control, it's this idea of the slow system and the fast system. The inner loop is the fast system. So you have the outer loop, the voltage loop. The voltage dynamics is going to be dynamics. Yeah. The fast system, you can obtain the boundary layer, changing time coordinates, and what you obtain, or what you're doing is simply looking at in the fast dynamics, the slow system is almost a constant. So if you consider this dot seed equal to 0, this dynamics here with this change of variable, time variable, you obtain this is a fast dynamic. So well, if you look for information about PWM DC to DC power converters and design of this kind of controllers working with this kind of system, and the singular perturbation approach, you can find the following. In this 3 reviews by Saxena and co-workers, Naidu and co-workers, from 1984, 2002, and 2014, we have more than 3,000 references. We have more than 1,300 references, but you only have 3 papers concerning design of controllers or design of PWM converters. These 3 papers, one of 2008, which worked with power factor correction by Kimball and Crane. And in the case of control and current mode control, we have 2 papers by 2 Mexican guys, Alvarez Ramirez and Espinosa Perez, which work with the stability of current mode control. So for us, it was a very interesting subject to work with, and I'm going to explain what we are doing here. This is the kind of model we are working on. Here we have the L and C parameters of the converter. If you remember, PWM DC to DC converter are composed by inductors and capacitors. So these are the values of inductances and capacitances. Here is an energy transfer matrix, and here are the resistances in the circuit. In this case, series resistors in the case of inductors, and parallel resistors in the case of capacitors. And well, this is the way the voltage source influence the converter. If you look at this as a differential equation, you can obtain, in this case, in this average model, you can look for the equilibrium point. And well, from here you can obtain this, fixing this duty cycle. So, well, with these 2 terms, we are working now what we are going to do with the current mode control. Here, this is the same model, but look at this. Inductances and capacitors, you know, they are very small. So in this case, you can use it as the fast variable in the singular perturbation approach. This is the first difference, or the most important difference, with respect to the work of Álvarez Ramírez and Espinosa Pérez. They were working AI with in this case, a gain of the integrator. We have here the power converter, and this is the current mode control. Here we have a proportional controller with an integral action here. Yeah. And in the case of only integral control, you can reduce this system, this complete system, only, you know, here you have this intermediate variable. In the case of integral control, making this 0, you cannot directly obtain from this integral controller the duty cycle. Yeah. Well, in this case, in the paper, well, it is a little bit more explained with in the case of current mode control. In the following video, I'm only going to work with the integral controller. Here, well, first, in this case, we have this will be the path dynamics. This is the flow dynamics. And what I am going to establish here is the stability of the path dynamics. This is quite easy. This result is, I think this is very well known. To demonstrate that the system with a constant controller, that is the idea here. If you have a constant controller, this is going to a unique reference in a very smooth and a very stable way, asymptotic in this case, with asymptotic stability, and this is a demonstration. You have to obtain here the exact aerodynamics, and using this the Lyapunov function candidate, the result is more or less direct. What we do here is you fix the controller of the duty cycle to a constant, and the result comes from the LaSalle's invariance principle. For example, if you have resistance in any element, inductors and capacitors, this is less than 0. If not, in the case of the following converter, you are going to see this. You can use this invariance LaSalle principle. Here an example, and this is to show what is going to happen to the flow dynamics. Here we have the path dynamics and the flow dynamics. How it is going to work? Well, in the case of the low dynamics, this is going to be fixed at the value of the equilibrium point of the voltage converter, of the output of the capacitor, which is this value. Taking this into this equation, we obtain an autonomous equation which is stable, smoothly stable. Well, from a complete proof, where we have stability here and we have stability here, and there are a lot of work by Halil. Working with the, well, now you have to define compound diagonal candidate, and you obtain, well, stability, asymptotic stability. I am going to show you some experimental results with this boost converter. We are measuring current only for the purpose of well, you know how it is going, where the current is going, and what the controller is based only on an integral control of the output converter. Well, we have now I'm going to show you what is happening with this controller on the regulation in the against variation in the power supply and the load. Here in open loop, these are the results on the load variation, and these are the results on the source variation. Well, why open loop? Look at the velocity. Well, this is very fast because of the dynamics, natural dynamics of the boost converter. The problem is that it is not robust. We are not going to the desired value, so you have to use closed loop control. The problem with closed loop control is now, you want this to work in a robust way against this kind of variation. Well, in the case of integral control, this works very nice. Yeah, this integral controller works in a perfectly so more or less at the same velocity, or in the same the time settling is more or less the same in the case of the open loop control, and in the case of variation of the current of the voltage source, this the result are not so good. What is happening here? Well, we have an integral controller at the end of the converter. The load variation are very close to them, so this works very nice. But the source is in the point far away from the controller, so the results are not so good. What you can do here? You can do nothing. You can with the integral controller you can do anything more than this, but if you change the dynamics of the converter, this is going to work this way. You can obtain a faster. Here in red, you change the controller. In the black picture, you change the controller. In the red, you change the dynamics of the converter. And look at this. Here you have a better dynamic than before. And this is in this case you are obtaining an integrated controller. I mean, my time is almost over. We have here some remarks and conclusion. We revisited the work of Álvarez Gallego. We're working in another form. We're working with the natural dynamics of the system. Maybe the problem here is, what we are showing also, this is very robust, that has its limit of performance. The limit of performance of this kind of system are the open loop dynamics. This is my limit. In the case of four-order converters, if you are only for current mode control, if you are only measuring the internal current, it doesn't make sense because of the dynamics. The natural dynamics is the same as without measuring the current. And we have obtained an integrated design back and forth, working with the LC parameters and the So one fast question later. We are going to work now with the following presenter, following speaker. Yeah, the next presentation. Yeah. Huh? It is.
No, no.
No, this is not the good one. Thank you. Now, Humberto. No? Yes. There. Yes. Humberto. Analysis, yeah. No. Optimization. Yeah. PDF or the other one? Let's see, I take the pen. Let me see. Let me introduce our next speaker. He is Humberto. Yeah. He is Humberto Bolaño Cerrut. He is a mechanical engineer graduated from IPM, Escuela Superior de Ingeniería Mecánica y Eléctrica. Currently, he is pursuing a master's degree in electronic engineering at the Instituto Tecnológico de Orizaba. Please, Humberto.
I'm going to I'm going to explain you an optimization algorithm for accurate frequency time rate PWM generation with microcontrollers. Okay. These are the contents. I will see. As introduction, I can say that the PWM is a technique widely used to control electric or electronic devices. In my case, I'm working in a three-phase 9-way inverter, and it requires a kind of PWM that changes its duty cycle every period. So that happens different. Out of that PWM period, we get a sine wave. One essential parameter to consider when using microcontroller PWM to modulate signals is a parameter called frequency modulation index. And because the frequency accuracy of modulating signal depends on the proper calculation of these parameters. And this algorithm makes the proper calculations to select an appropriate frequency modulation index for the implementation of microcontroller. First, I'm going to explain how PWM can be used to generate the whole time wave must be divided into smaller periods of record duration. Because each year is divided about 30 samples. We will call each smaller period a sample. The PWM period equals to dividing the time wave period by the number of samples we want to divide the time wave into. In the same way, each sample must also be divided again into smaller periods. In this case, the period can be a microcontroller clock period or a prescale. If we want a better duty cycle precision, we must divide every sample into more clock periods. So if we have, for example, we get a smaller duty cycle change. In the case of the PWM, the main role in time wave generation is the ability to change the duty cycle every period, so that the average energy for each period is equal to the corresponding time wave sample. In this case, we can see a sample pointing to about half the PWM period. So in this case, the sample, we would need 50% recycled. And okay, so we know now that the time weight is divided into many samples, and each sample is also divided into many. So the total time weight period can be expressed as this equation. We multiply the PWM period in dot cycles by the sample number, and we get the time weight period in dot cycles. Since we want, or well, or rather want to calculate these two parameters, we need to first know the value of the time weight in dot cycles. So we must divide the dot frequency by the time weight frequency, and by replacing this part in this equation, we get this equation. And this equation represents all the parameters related to the frequency modulation index. And our algorithm is designed to calculate these two parameters to match exactly or near exactly this relation, this frequency relation. To make a calculation, we have some constraints that we must consider before making calculation. First is that we can only digitally represent their values. This is because the timers can only count to their values. We cannot use decimal values. And it must be also emphasized that the fact that increasing the PWM period unavoidably implies decreasing in sample numbers, and vice versa. If we increase the sample numbers, we must decrease the PWM period to maintain constant these relations. It is also not difficult to select PWM period too short, neither is it to select sample number too small. This is because if we select a PWM period too small, we can make specific type of variations, and if we choose a small sample number, we don't have enough information to review the planning. This is the block diagram of my algorithm. It is composed of 6 models. The one in blue. The objective is to calculate, as I told you, the PWM period and the sample number. As input parameters, we introduce the slot frequency and the phase frequency. And we want also a reference parameter. I will tell you how this all works. Here's the tip of the document. Is programmed to generate a prime number matrix to use in this model. This model uses trial division to find the prime factors of the given number here. This number is calculated from this relation. Then we have a combination of number calculators. This model gives us the number of combinations that can be made with the factors, with the parameter factor both. Then this is the model called the multiplication partition calculator. This is focused on building every possible multiplication partition, and then it stores the variables inside the matrices. Which one is the bigger numbers matrix and the smaller number matrix? And then we have a multiplication partition finder, which tries to find the better partition. I will try to explain a little example, small example. In this case, we require a phase frequency of 5 0.5 hertz using a clock frequency of 16 megahertz. The restraint parameter is that one of the numbers must be between 360 and 800, and this number will be used as a range number. First, we use the clock frequency and the phase frequency to obtain this number. Oh well, in this example, I'm going to explain you the second iteration, because the first iteration has about 20 prime factors, and this overflows the memory of the microcontroller. So I'm going to explain later why the algorithm is designed to catch that calculation in the case of having more than prime factors. Well, first we generate the prime factor matrix, the prime factor matrix. Then we calculate the prime factors, which are 3, 11, 13. Then using these numbers, we calculate the possible combinations, which are 4, 7. Then we use this to find the partitions. When we get this, there are 7 partitions. Then the algorithm is the algorithm choose one of them. In this case, the algorithm is designed to choose the numbers which have the less difference between the two numbers. We choose this number. Then we use the feedback loop to check if it meets the restraint parameter. In our requirements, we have two segments. There are the requirements to just run the algorithm and obtain the result, or the requirement to just run the algorithm and obtain the result, and also be able to implement the calculation parameters. To just run the algorithm, we can use the algorithm in every microcontroller and obtain the result, but we must take into account that the memory is limited because, as I told you before, the factors can only be calculated as a limit. We just run the algorithm and obtain the result, and also implement the result in a microcontroller. We also need a 16-bit timer and enough operations for the cycle. In the PWM, in the calculated PWM periods are all bigger than the value that an 8-bit timer can go to. We need a 16-bit timer. These are a little table showing some of the results and some of the calculated frequencies. We use it to dot and 18 megahertz dot and 16 megahertz dot, and we tested with different frequencies. This is the frequency we get using the algorithm. And these are the parameters calculated: the PWM period and the sample number. You know, the bigger the frequency we want, these two numbers tend to go smaller. So to implement this algorithm to generate frequency bigger than 120, we need also a bigger top frequency. But these numbers tend to be smaller. So that's all.
Thank you. Well, questions? that this algorithm can be functioning to this microcontroller. It also with APIs. No, this algorithm is using English microcontroller. Another question? Umberto, please, if you, well, you may explain that because you are, what is the reason you are working on this precise accurate frequency in the case of the station power return? Please let us know. Because I'm going to implement a three-phase time wave inverter, and I need to build also the control segment. I can generate segments that can also be accurate to obtain a desired frequency. Thank you very much. We are going to thank Humberto Bolaño Cerú. And here we have a proof of participation from the Silver staff. Thank you. Thank you very much. Our next speaker is Mr. Arturo Soriano. Yeah, this is analysis, yeah? And now, here and there, and now, just a second, let me present you. Here you are. Dr. Luis Arturo Soriano is a postdoctoral researcher en el Instituto Tecnológico de Estudios Superiores el ITESM, Campus Ciudad de México. He participates in the Binational Laboratory on Smart Sustainable Energy Management and Technology Training. He received his PhD degree here from his house and here in the staff in automatic control in 2015. His line of research are power electronics, renewable energy, and artificial intelligence. I did analysis of DC-DC converter for photovoltaic application, vision on conventional DC algorithms. This is the outline. I'll give a little introduction, the problem statement, the objectives, the modeling of cell and PV panels, the MPPT controller, the design of the CDC controller, the DC-DC converter, classical MPPT algorithms applied to DC-DC converter. Then I present some results, and the last, the conclusion. In recent years, the installation of capacity of production of energy from solar panels has increased, as we can see in this figure. Yes, but not just in large utility scale. It's also in residential and commercial applications have been increased. This graph is a case of study in US. US represents the second country around the world that produce with 23% of all the world solar energy, just below of China. And until 2010, here, the most common topology of used solar panel was a string inverter, where each panel connected in series. But this topology implemented in residential and commercial application not function very well, because with this string, with this application installed in of the house, each installation functions in different ways in residential and commercial application.
And then now the power optimization topology has been interesting because in this topology we use DC-DC converter connected with each panel, with each solar panel, and this has some advantages. One of them is increased efficiency. The life of time of PV panel has increased, and just and then this topology has some disadvantages like the cost is very high in comparison to classical topology string inverter. And in this sense, this board is related to find a framework to select the best DC-DC converter. In this board, we prove this with conventional MPPT algorithms. And the problem is the next. The residential and commercial installation operate with different yields and positions and require extract the maximum power. That means if we have two installations with the same capacity, but this capacity are in different yields and positions, I can extract the maximum power because these two variables, and this is a problem. And another problem is that the same as DC-DC converter should be considered size and cost of implementation because this topology is good for this application, for the residential and commercial application, and as is necessary a framework of reference about efficiency and tracking the speed of MPPT in DC-DC converter photovoltaic application. In this sense, this work is use this modeling of one cell when the production of energy occurs when the photons are absorbed in the junction and then free electrons, and this can be represented by source of current, the other bypass diodes, and shunt resistance and series resistance. That this circuit represents a one cell. Then we represent a PV panel. PV panel is in our arrangement by cells connecting in series and parallel. In this sense, we can extend this model in this way. This is the one cell, and this term represent the number of cells in series and number of cells in parallel. And in this work, is considered a real PV panel from Sensotech brand with number of model SE 19P with 36 cells and with these values of maximum power, voltage, current. Now, MPPT controller, the features of MPPT controller is that the MPPT controller works with a DC-DC converter. The MPPT controller sends current and voltage from PV panel and adjusts in online duty cycle in order to get the maximum power point. And then this MPPT controller can be worked with in a standalone way or grid connected. Then of MPPT controller can be used here battery in a standalone application or an inverter to inject a produce of energy to the grid. In order to analysis and comparison DC-DC converter for power optimization optimizer topology, it's difficult to do a comparison because each DC-DC converter has different features
to work at the same power. In this sense, we can compare it in inductor, in size inductor or size capacitor, or the same frequency. We compare this converted with the maximum power filter. In this sense, this design of this each converted was developed in order to find the maximum power point. And in this diagram, we can see the MPPT controller using an algorithm. Here, an algorithm in the literature exists several MPPT algorithms to get in order to get the maximum power point. One of them is perturbation observation. This algorithm sends voltage and current, and then get the power, and this power is compared with the new sensing of power with the last sensing power, and then ask if the new voltage is greater than the old voltage in order to modify the step of duty cycle. This has a problem because you need design this step very fine, because if you design this step very short, this point can be part of this side, or if the point is here, this part of the other side, and the MPPT is not fine. In this sense, this algorithm presents some advantages, like easy implementation in a microcontroller. Another is present some disadvantages, like oscillation around of MPPT, but for the size of the step, this step, we can MPP in this side and this side, and then this side of the step side depend the tracking speed. That means if we design this MPPT algorithm with a small step, we have a wait time in to find an MPP. But if this step is designed very high, of course oscillation around of MPPT. This is the first one, and this is the second algorithm, incremental conductance. This algorithm works with the derivative of the variable in order to find the maximum power point. In both case, we find the maximum power point at the standard test condition. That means with some condition of irradiance, or some condition of temperature. But in real application, this is not possible because the sun varies, and unless this behavior is different. But in order to get this, the main objective of this work, that is find the best DC-DC converter, is considered two features: the constant current, the constant irradiance, and the constant temperature. And then incremental conductance works with the derivative. If the derivative is major than 0, is of this size. If derivative is minus of 0, is of this size. And if derivative is equal to 0, the maximum power point is here. This algorithm has some advantages that offer good and rapid changing, offers a good MPPT under different or changing atmospheric conditions and oscillate and it has lower oscillation around MPPT as compared with piano. Then we simulate the DC-DC converters in order to find what which one is better under the same conditions, changing irradiance and temperature, just these two variables. And we find that in the case piano, the best response is boost converter, and the second one is boss, and the third one is book boss. Book boss is the medium that oscillate around the MPPT very in a medium way, but it's important to remark this because in this application, in a normal operation, this topology requires increase the voltage or reduce the voltage. It depends on the hour of the day. And in boost and boss converter, just reduce or increment the voltage. And the Cook and Sepik, the Sepik is bad response because oscillate very high around the MPPT in comparison of book and boss. And remember that book and boss, the book and Sepik converters are types of book boss converters. The second result is incremental conductance. We can see that the response is the book converted to. But if we have application of power optimizers, we require book and box converted. In this sense, we can see that the incremental conductance algorithm oscilles low than piano algorithm, and this get the same oscillate very low around the MPPT, but this algorithm get the minus power in comparison with the piano. We can see the case of book box converter, 79, and then 77. In this sense, with this comparison, we get the next feature: efficiency, high tracking speed, and oscillation around on MPPT. And in this result, we get numbers of components. It's important in order to reduce the cost of the application for MPPT for power optimization. Sorry, and then the next features, the response of change, irradiance and temperature, tracking oscillation, and efficiency are three. These features are important in order to design a good MPPT controller based on DC-DC converter. Response of change, incremental conductance responds very fast in book and boss. In book boss, response from medium to low, and tracking oscillation speed. The same way, incremental conductance has a low tracking speed in comparison of piano algorithm. But in efficiency, incremental conductance has lowest efficiency in comparison and piano algorithm. With this, we generate a reference framework in order to take decisions when we design DC-DC converter to different photovoltaic applications. The efficiency is better in P&O algorithm, but this is a framework with respect power electronics, not with MPPT algorithm, because in the literature it exists several algorithms that increase the efficiency of this algorithm. That's all. This is research funded by National Laboratory on the Marques Sustainable Energy Management and Technology Training. Yes. Thank you, Arturo. Are there questions? Well, well, it's quite difficult to me to make a comparison in this case. Yes, you are basing your comparison in the case of power, but they are nearly the same. I mean, no. Well, let's go to the almost last, the following one. The following one here. They are almost, well, not there. There is not much difference in efficiency. Yes, I mean, but this is for one panel. Imagine if you have an array of panels, and you have to choose them back and boost converter. This is your result. Final result. Boost converter is fine in order to reduce the cost, and you can use to elevate or reduce the voltage. Depending on the application can be standalone or disconnect. But in a real application, you have to make the real application. The real application in large utility scale until 2010, this is the most common topology, steam inverter. In this sense, we always need to reduce the voltage and inject the grid. Yes. But now with the residential and commercial, you can small string solar PV panel, and you can reduce the depend of the hour of the day. In the morning, you can reduce the production of energy, and the afternoon rest because we use minutes than the morning. This is the main objective of this comparison, and the future of we compare in this work is a power, because the duty cycle is different for each one converter, the size of the inductor and the size of the capacitor and the frequency is different in order to get the maximum power from silicon. Thank you very much. Another question? No? We thank Luis Arturo Soriano. And here we have from the CCE, CCE, your proof of participation. Thank you, Luis Arturo. You see, yes, our next speaker, and I'm very happy that all the researchers here is me. Here, the younger ones are working very hard. I'm very happy for that. Now, well, this one, yeah, the past, this is it. Yeah. Let me introduce our next speaker. You have your, and just a second. Yeah. Let's see. Marco, un segundo. Marco Carvajal Retana. He graduated in communication and electronics engineering from ECIME in Huascan. In 2016, he is currently pursuing a master's degree in the CCE for graduate studies of the Cine Culhuacán of IPM, Mexico City. Since 2014, he has been participating in several research projects of IPM. His current research interests include CD to DC power converters, wireless power transfer, and mathematical numeric modeling of power converters, I think. Thank you, Mark.
The design methodology of integration and space the converter supposed to be present. Outline, introduction, objectives, the topology of boost converter, multi-phase, multi-stage boost converter, an example of design of this topology, simulation results, and finally conclusion. Introduction. Today it's possible to wirelessly power for reshaping electric vehicles using renewable energy sources and using CCE to DC converters to obtain the DC level to stable values. The objective is design of DC-DC converters to unite DC bus for high voltage and high current capacity with the highest possible efficiency using commercial elements. Here is the topology capacity of boost converter. Here graph is the British icon where if increase the duty cycle, the gain increase too. For example, calculate the duty cycle of boost converter with the next specification with input voltage 12 volts, output voltage 100 volts. The duty cycle is 88%. Assuming either converter, the voltage gain is 8.33. If the current in load is 1 ampere, the current in the voltage out is 8.33 ampere. The MOSFET must be capable of any high flow current. And finally, this is high stress in the MOSFET. Here is the topology proposed. Multi-phase, multi-stage to convert. Here is the first stage, second stage, and then end stage. This is the first stage, second phase, and then end phase. Example of design with these parameters is an input voltage 12 volts, output voltage 100 volts, output power 100 watts, duty cycle is 20%. This value is proposed according to this graph. This graph is obtained the frequency tuning. Is reporting in the article advantage of multiplication regulator, where the duty cycle for three phases is the current difference is close to 0 if the duty cycle is 66%. The voltage difference is 10% of the voltage. Working play the phase shift of signals is in each phase 360 degrees is divided by the number of phases. In this case, the phase shift is 120 degrees. Using the third table, we can see the minimum number of elements that is the state during the interval time interval is 2. This parameter is called T. Here in this table presents the equation to use it. The first step is to calculate the number of states. In this case, it's 2. After calculate the output voltage for the fifth stage, in this stage is 30 volts output voltage. The lowest equivalent for this stage is 9 ohms. The current in inductor 3.7 amperes. The current report 0.74 amperes, and the value of the inductor is 115 microfarads. Output current 1.8 milliamps here, and the output capacitor this is very small. The time parameters for the second stage, the input voltage is the output voltage of the previous stage. In this case, it is 30 volts. The output voltage 100 volts. The battery cycle is 20%. Output voltage report 10% of output voltage. The power 100 watts. The frequency 100 kilohertz and 3 phases. The equation is the same. The velocity in this case is 100 ohms. The current in inductor 1.1 amperes. The reference current in this inductor is 2.2 amperes. The inductor is 945 microfarads. The output capacitor is 53 nanofarad. This is the schematic with the obtained value. Is the topology with the first stage and 3 phases. This topology is used in the simulation with parasitic elements for obtain measures with losses, with these losses. Here is the current in this phase for the fifth stage, where this current is shift with phase shift corresponds to the 120 degrees. The output voltage for the if the state corresponds to calculate with voltage difference is 10% of the voltage. The current is traced for the second state. The output voltage of the second state, and this can be corresponds to the 10% of the voltage difference. Is the 10% of output voltage. Finally, the output and input power, where with the RMS value, calculate the efficiency of 89% of efficiency. Finally, conclusion. A design methodology of multiplication displays the body with reduced current and voltage display in 15 devices for the reduction of the duty cycle in CDM signal is validated with the use of small steps, dividing the gain in multiple steps. We finally obtain a converter with the current and voltage response. To increase the efficiency in this converter, we suggest incorporate
Thank you. Sorry. Well, thank you, Marco. Is there any questions? Please.
I don't know why it's important to reduce the WLB cycle. Why I see that conclusion. We propose this cycle according to this graph. One advantage of this topology is that reduce the duty cycle because the gain is dividing in the state that finally is reduce the timing in a state on a state these devices and reduce the stress.
You can come in a bit, Leonardo.
The topology is to reduce or application in widely. In this case, when I use power energy with it, and we have higher stress mode, and the topology proposed for Marcos to reduce and help itself more efficient and input with elements with more commercial.
Is there some kind of trend which shows how we use it? I think it's a model of efficiency. But I don't know. I for example, I'm aware of communication losses. The communication losses will be almost the same, independent of the big type of communications in so fast. So I don't know how the semiconductor is more stressed. The frequency is actually the same. Definitely level in the level of this voltage and yeah, right, because the raw power is taken first. Let's say reducing the duty cycle is not what makes this possible. Reducing the power among the devices and a consequence to reduce the duty cycle.
In this case, like this. This is the top. The application is to obtain one kilo. But in this case, I presented the prototype of 100. When I obtain the 1 kilowatt, the voltage phase and current phase it's a project. We need to reduce user cycles in Moses to order to obtain high efficiency with lower but I simply next please. Another comment, Marco? I don't know. Another question?
Well, this was the last presentation today. We are going to thank you, Marco and Eduardo. Thank you very much. Well, thank you very much for being here, all of the attendees. It was very nice to see a session with younger strangers. Well, younger than me. But well, this is I think the CCE is the nicest scenario to be here for people from outside, also from Peru. And well, thank you very much for being here. See you and well, enjoy the conference. And thank you very much, Enrique and Oscar, Lucho, etc.
Vamos a darle ahí un